Last time we talked about linear regression as the beginning of that segment. So if we go down, then you did some exercises. There will be more time today for exercises, and there will be exercises on non-linear regression, but if you're not done with this on linear, you can, of course, do that. Make it a little bit bigger here. And those were the exercises, and then we are here. So today, the topic generally is nonlinear regression and nonlinear models in machine learning. And we have a little first example here, which showed up earlier as well. This is a weather dataset or climate dataset with some weather measurements from a weather station in Delhi in India. And it measures its mean temperature, humidity, wind speed, and pressure at the place in that city. And it's the mean over a day, so it's one measurement per day, and it goes over several years. So we have you can download the data set there, and we will use this as an example to see how you can do machine learning in Julia. Anastasia already showed you some ways, but I will do it in a slightly different way. We can see if I copy that code to VS Code here. And what do we have here? This is a little bit about loading data sets and plotting them. We have seen this before, but this is a CSV data set. So you can use the package CSV and CSV read. You give the path to where you have put your data, and you get the data frame out. And we can form a matrix of these four measurements. So it was the mean temperature, humidity, wind speed, and pressure. We can give it some titles, and these are the units, so labels for the graphs. But there's an interesting thing here which you might not have seen. It's if we have a matrix, this is really four different things. And I want to have four different graphs in a kind of layout. And then you can use the keyword layout here. 4,1, it's similar to, I think, pie plot, where you have, this is 4 rows and 1 column. So we have 4 plots on top of each other. We can plot this and see. So it looks like this, pretty neat. You get to four graphs or 4 plots stacked on top of each other, and this looks reasonable. Everything except this one. So here is a common situation where you, the unit here is hectopascals, so 7,000 or something. And air pressure, so normal pressure at the surface is something like 1,000 hectopascals. It's a little bit more. And but it doesn't vary that much around that. So 7,000 is completely unreasonable. So this is a measuring error. And there is some other stuff down here which is pretty large as well. So there is some noise in the data, you can say. And what we can do, so let me show you that. This is just that graph here. You can filter the data for things that you want to remove. So not just, we saw before, we saw drop missing, and maybe fill in some value where something is missing. Here we have measurements, but they are wrong clearly. So if we take the same code here, but I added 2 lines, you can filter a data frame. If we take the mean pressure, and we say, I mean, it's reasonable to, if you take 1,000 hectopascals, so plus minus 50 or something like this. That's close to the records of max and mean pressures ever recorded. So if we take the values that are less than 950 and we replace that by, say, not a number, you can use this object. And we do the same thing with the values that are more than 1,050. So kind of filter in there. And then just do the same thing as before. We can try that. See what happens. I copy that to VS Code here. I'm going to need my path to the data. And now it looks sensible. So the only thing that changed is the pressure here. So all of those values that we see now, they were sort of close to the 0 line there. So you see the values here are around 1,020, 995, and so on. What happens here if you do like I did, just replace with not a number, is that I mean, those rows are still in the data frame, and the temperature, humidity, wind speed measurements are there, but here there will be sort of holes in the data when you plot it. So it can be a good way of doing it. You'll just not see it there. That's the same graph there. Okay, so now that we've loaded the data here, we want to test some nonlinear regression methods to do something with this data. And what I thought we should look at is, I mean, if we look at these 4 here, one might imagine that there is some kind of relationship between these. For example, that one of them you may be able to model as a function of the others. So we'll do that. For example, the temperature here might be a function of humidity, wind speed, and pressure, or one of the others, a function of the other 3. And so we'll try that to say model the temperature as a function of humidity, wind speed, and pressure using a nonlinear model, and in this case, a neural network. So I want to talk a little bit before I go into that example about neural networks and some terminology there. So this will be a recap of what Anastasia talked about, but from a slightly different angle. So let me see. I have some slides here that you can download, look at later. So I'll show you that now. So I got a few notes here on machine learning, and so we talked about neural networks a bit, and I want to go into maybe a little bit more detail. I mean, the general situation is that we want to learn a function or a relationship between input data and output data. And in our example, we have input being, say, humidity, wind speed, and pressure, and output is the temperature. And I depict this as this f here is the function, and I got input and output there. And for f itself here, we often use a neural network. We will also see some other examples later of other types of models. We saw linear models earlier, but we'll see other types of nonlinear models. And neural networks are so-called function approximators. So they can in principle mimic any function, any nice enough function, let's say, if the network is big enough. And from another point of view, you can say that the network can describe many different kinds of functions, and we need to find the right one, or at least a good one, the one that's good enough among all of those functions or relationships that the neural network can describe. And this picture here is a kind of usual picture of what it looks like on the inside here on the neural network, but I'll return to that in a moment here. So the key thing here is that the model, that for me is the neural network itself, it depends on a bunch of adjustable parameters. And so these parameter values are what determine which function the model will describe in the end. And that's also what's adjusted during the training phase. So you have these parameters, and when you do the training or learning, that's what's changing and adapting. Now, neural networks are built, and this is one of the things that are interesting and useful about them, I think, is that they're built as compositions of simpler parts in a kind of network. So you can see it as a bunch of layers here, as in the image. You have layers followed by other layers. And each layer is a linear function, or more correctly, an affine function, together with the so-called activation function. And that's the nonlinear part. Activation functions are typically sort of on or off type things, that either you let through the signal or you don't, or some smooth transition between the two. But this composition in simpler parts actually facilitates computation and analysis, I would say, because you can use things like, you might remember from a long time ago, the chain rule about composition of functions and things like that. So often the situation we have, if we think about the machine learning problem, is that the data comes in input and output pairs. This is not always the case, but this is the supervised case. So we're talking about supervised learning. And you have these input and output pairs, and the network is supposed to learn from these examples of input and output and be able to generalize from that to sort of extract the rule or the relationship from that and be able to generalize a new such inputs and be able to produce the output. And as we mentioned earlier, we often split the data we have in training and testing. So we use part of it for learning and give it to the model for the training phase. But we keep the other part unseen, not used during training, and so that it's tested on data that it has not seen yet, so to speak, or that has not been used for training. So another element here which is crucial is the so-called loss function. And this is a measurement of how well the network is doing. So how good the network predictions are. This is measured with the loss function. And one example of this is the mean square error. And this is very similar, actually the same as the one we looked at back in linear regression. So we have our data points, input, output. We have our model, so we can make predictions on those inputs. And then we can measure how far we are from the actual data point with the prediction. And we square those basically to get a non-negative number, and we sum up everything. So that's the measure of how close the predictions are to what we're supposed to get. And if that's 0, it's kind of perfect, even though that would be rather dangerous because then we would be in overfitting territory. But overfitting is when the model is well adapted to the training data, maybe very well, but when you evaluate on the test data or new things, it's bad because it has adapted very closely to the somewhat arbitrary data that you have sampled from the distribution that you're interested in. So that means in a sense you don't have enough data, but you ran the model too hard on the data you have, so it adapts. Sometimes we say that it adapts to the noise that's in the data. But let's see. So that's the loss function, and the task here is to minimize the loss function or make it small at least. So we want to find a set of parameters such that the corresponding model performs well on the training data and the test data as well. And I have a little bit of details here on the optimization algorithm, because we say we want to minimize the loss function. That means the problem is an optimization problem, as in minimize or maximize functions. I will not go through this in detail. I think it's better that we move on to the exercises. But in short, it's you have these parameters, and as I said, that's what's being modified during training. And you start out at a random set of parameters according to some distribution. And there the model will be very bad and the loss will be large. And then you sort of gradually adjust the parameters all the time, measuring the loss, how well it's going, and moving in a direction where it becomes better and better and better. Or maybe it becomes a little bit worse and then better again. But and then you stop at a place where you're satisfied with the loss value. Okay, so let us do this. We look at this example here, and then we do some exercises. So returning now to what I was talking about, I was talking about modeling temperature as a function of humidity, wind speed, and pressure in this weather dataset. So we're going to use a neural network for this. That means that the neural network describes the temperature as a function of the others. And for this, we'll use, as before, we'll use first here the flux package. And we can go through the code a little bit. The first part here is the same as before, basically. We just load our data. I do a bit of normalization here. You can look at that later. We partition the data into training and test. So we got training and test datasets. X here is the things you put into your neural network, humidity, wind speed, pressure. Y is the stuff you get out, so that's temperature. There is a parameter here called to predict. You can put one of the others there actually if you're curious what happens if you want to predict something else. This is a little function to draw the results, to plot the results, so we don't have to bother too much about that. Here in Julia is an example of a neural network. So init flux Gloraux uniform, this is about the initialization distribution of the parameters that I mentioned. So maybe not the most crucial thing, but this one is the neural network. So we use chain, which is composing the simpler parts of the neural network together. And the simpler parts are these lines here. Flux dense is a dense layer. Dense meaning all the connections are there. It got 3 inputs, 10 outputs, and tangent hyperbolicus is the disactivation function that I talked about. Bias means it has a constant term in the linear function. And actually this one has one layer here and then one output. As you see, I have experimented with some other inner layers here as well, but they're not needed to get a good result. Loss function, it takes the model X and Y and it compares the prediction on the input with the Y values here. And we can use flux losses, mean squared error, as I mentioned before. To do the training, set up the training set, the optimization state is a kind of initial state of the optimizer, and we use the same as you've seen before, Adam, which is one of these gradient descent optimizers. And we're going to do the training for 1,000 epochs, so we're going to repeat the training phase where we adjust the parameters gradually 1,000 times, and this is the training loop. And the command, I think it's similar to the penguin example. The command you use to adjust parameters in the training is called train exclamation mark. You need a loss to model the data and optimization state. And then I compute also the losses or the square roots or the root mean squared. And I push those to a vector in order to be able to plot the loss afterwards. So it's a little script here. Can copy that to the VS Code and see what happens. Make it a little bit big. Okay, so that was pretty fast actually. Now it's going through the training. And there we go. Okay. So we plotted at each epoch, we plotted the root mean squared, the square root of the mean square error of the training and the test data. So it's a little bit larger on the test, and we get these results in the end, 2.3 and 2.8. So you can always think a little bit. I mean, this was temperature in Celsius, and so this is the mean error, you can say, 2.3 to. So that means 2-3 degrees, and the values were around 20. So that tells you something about the magnitude of the error. And so I got the plots here. This one was hiding beneath the other one. This plots the. By the way, this could be interesting before we jump to the exercises. What did I do here? I took the training and test data. I used the function partition, and I took 70% training, 30% test. But I didn't do this shuffle. If you do shuffle true, you get randomly split in 70-30. But I took false. That means you take the first 70 for training and the last 30 for testing. So I think that makes more sense in this kind of situation where I'm using the first few years for training, and then I want to predict on the last one or whatever I have left for testing, instead of mixing it up. There's a question of overfitting there otherwise. This is a harder test. And what do we got here? We got training data in blue. We got prediction on the training data in, red or brown. We got green test data, and we got purple prediction on the test. So, yeah, it looks reasonable. It doesn't really pick up these peaks here, but maybe you have to do something more to get them, or use a different kind of model. But the error we got is okay. This is the losses plotted against time. So here you can see it goes down. Actually, not so much happens for the last 500 epochs here. Yes. Just very quickly, because it's kind of useful to know. Uh, Instead of doing the training and plotting this at the end, you could do an animation of this, and just to see how kind of convenient that is in Julia. If you have this training loop which went through the epochs, instead of doing that, you do an animation object, and then you do your for loop and tell it also to save every other or every second frame. You can do a little animation like this. So this is the evolution of the predictions. I mean, we get different models all the time when we do this training, and it will have different predictions. The blue and the green will stay the same because that's the training and test data. This is the beginning of training, so it's not very good, and then it bounces up here uh, and gets better and better. You could also see how the loss went down very quickly there at the beginning, and then not so much happens here. So that could be an illustration, a way to visualize what you're doing and what's happening. Okay, I think I have one more thing about that, but I think we'll jump to the exercises and then I'll show you that later. So let's see. I have some more examples here, but then there are exercises down here, which you can go to directly. And should we say 20 minutes? Okay, so we saw that example with the nonlinear model for the climate data. I also included here, this is just to remind you that maybe you don't have to jump on the first linear neural network that you see. You shouldn't forget the linear models or simpler models. So I have an example here where we try to just do the same thing with the temperature and the three others, pressure, humidity, and wind speed, but with a linear model instead. So if we do, that's the next example after that animation. So we load the data the same way and create X and Y as before, humidity, wind speed, mean pressure, and mean temperature that we want to predict. But we also split the same way in training testing, and we set up a data frame with three columns for the input variables, the independent variables, and one for the output variable. And we use a linear model like before, so use LM and the GLM package with this formula, which is 1 plus the three columns. And there's a similar function as before to plot the results. We can see what we get. So if I copy this, let's run this. There. And that looks pretty good too. As a comment here in the chat about plotting the residuals, that's also a good idea. Then you take the difference between, say, the blue and the red points and the green and the purple points. But we also print here the root mean squared error of the linear model. And we can see here that we got in the training 2.6 and on the test around 3. So what did we get? That's 2.6 and around 3. So what did we get for the other one? We got 2.3 and 2.8. So it's almost as good in the mean, at least, the linear model, as the nonlinear one. And actually, it manages to capture these peaks a little bit better, you can say. Okay, so let's move on from the weather data. I have another example here, which is where we'll use another type of nonlinear model instead of neural networks to see how you can do that with the Julia packages. And the example dataset here is the airfoil dataset. So these are measurements of airfoil, so blades, so aerodynamic blades, like in turbines or airplane wings and things like that. And they measure various aspects, but what we look at is noise created. These are measurements done in a wind tunnel, and then it has generates some noise which they're measuring. And so the fields here are, let's see, they measure the frequency of the sound that comes out of it, the angle of attack. This is has to do with the wind speed relative to the orientation of the blade. Certain aspects of the geometry, size of the blade, the velocity far away from the object in the wind tunnel, and this is another property of the flow field, and also the sound pressure level, which is scaled by a parameter here. But we look at the problem of, say, predicting the scaled sound pressure level from all of these other ones. And I think I'll jump to the slides there, because in this one we'll use a slightly different model than neural networks. So after this stuff with neural networks, I have two sections about decision trees and random forests. So you encountered this the other day also. But decision trees are piecewise constant functions which you use as a model. And this means that the way it's done, you partition the input space into boxes where the model has a constant value. Like in this example here, on this box here, it's on this level, and another box here where it's on another level. And then you use a greedy optimization algorithm. So greedy, this is similar to gradient descent that I mentioned. You try to improve things all the time. To define these boxes, which is defining the variable that you want to split on and where to split it, and also the output value in each box. And random forest is a variation of this, where you have many decision trees, so many trees make up the forest, and you do a so-called bagging model of this, where you take the mean value or the average result of many decision trees which are trained on different parts of the data. So we'll try models like this, decision trees and random forest. And I also briefly want to mention Gaussian processes, because this is something you might see in other contexts. So these are random functions or stochastic processes which can be used for regression. And they incorporate the Bayesian viewpoint, which means that you have a kind of prior guess of your model, and you modify it by the data, and you get a posterior. And what's interesting about this is that you get your regression model, but you also get the uncertainty of the prediction. So this includes, you can say, confidence intervals of the model, so how sure it is about the value. So if you look at this example here, it's got this blue line, which is the prediction, and it actually passes right through these data points. And there it's very sure. And then you have a bigger confidence interval outside where there's more uncertainty. But this is something that's I think in a lot of machine learning, when we have the model, we have reasonable result, and we apply it, but we're not sure about how confident we are on the actual predictions, and it's very nice to have a measurement of this. So that's a short introduction to those three different types of models. Back to this airfoil example. We want to predict scaled sound pressure from frequency, angle of attack, chord length, and so on. And here, before we used flux to train the neural networks, now we'll have a look at this MLJ, Machine Learning for Julia package. And here we also import the decision tree package. This data set, it's called the airfoil self-noise dataset. There's a link to download it here. And we can actually download the dataset here in the code using the HTTP package. So you give the path here and then do HTTP get. So it's a CSV dataset, and we read that in. And then we want to predict scale the sound as a function of the others, 1 to 5. And what I do here apparently is I do both a linear model and some non-linear model just to compare. So the linear model is done in the same way as all the other examples. We got the formula here, scaled sound is what we want to predict. Then we get frequency, angle, attack angle, chord length, and so on. We use training and test split, in this case randomly, and we have our training and test data frames. So the linear model we can get already now by GLM fit. So we store that in linear model. And for the non-linear one, apparently I do, let's see, yeah, this is the test set and the predictions of the linear model on the test set. So I want to store this for later. And also compute the root mean square error on that. And so that's for the linear model. And then for the non-linear model, we create our X and Y matrices. This is the scaled sound pressure, and this is the other ones. And then apparently we split it again randomly. We could have used the same test and training data points in this case, but I redo it here. It would maybe have been more informative to have the same one to compare, but you can also run it a couple of times to see how it behaves. I mean, it becomes a random process, but you can see the behavior rather quickly. So the model here we use, the non-linear one, is not a linear neural network, but a decision tree in this case. And you see here there's an alternative, a random forest, but it's commented out. So how do you use that? Well, you instantiate a model class, which is this decision tree regressor. And then you have to create a so-called machine, which takes the model and the input and output data. And then you can just do mlj.fit, exclamation mark. So on the machine, and you tell which rows you should use for training, and in this case they're called train. So that it's pretty quick. You just need these few lines to set up a model and fit it, and then do predictions with mlj.predict. And now we do it on the test set. So you pass rows equals to test there. We also want the root mean squared error to compare the results, and we print that. So let's see what kind of result we get. I copy that. This should be it. Yes. So that's it. We didn't plot anything in this case. We just get two numbers. And this is the root mean squared error on the linear model, 4.7, and root mean squared on the non-linear model is 3.2. So it's at least significantly better here. We can run it again with different test and training data. The linear one is at 5 and the other one at 3, and so on. So in this case, non-linear model is significantly better. And we can try here also the choice of model. I had the decision tree. I can flip that to random forest, so many decision trees, and see what we get. Now I got a little info here about.
Do you with support vector machines?
What was the question?
Do you have a model where you use support vector machine, SVM?
Support vector machines. Yes, you can do that too. So that's a very good question.
Thanks.
Let's look at that. That's a very good question. So this is with the random forest, we got 2.14. So that one is better actually. And regarding that question, this is something you'll try in the exercises, but I can do it here as well. If you want to know what else you can do, there is a convenient functionality here. The last few lines in this example, you can do for modeling models matching the data that you're using, and then it starts guessing what model you might want to try based on the data types. And I print those models and also which package they occur in. So if we run this, see if it works here. We got decision tree, cat boost, regressor, Gaussian mixture. Okay. Neural networks, random forest, and no support vector machine apparently. But I have another line here. So get more model suggestions by changing type of frequency. I think let's see, what's the data frame called here? It's called DF. Where's frequency? That's an int. And well, it happens to be kind of these types of frequencies that they have measured at 800, 1000, and then they have recorded this as ints, but this may not be the most natural thing for frequency. Perhaps a float is more sensible. So we can change the type here, frequency continuous, and then it will find more suggestions of packages. So let's see. Because here it thinks frequency should be an int necessarily, and then so here's a bunch of stuff. ADA boost. So what were we talking about? SVM. Yes, here. SVM linear regressor, support vector machine, some other regressor, support vector machine regressor. So you can try this one and see what the results are. It'll be very interesting. And it will be a little exercise you need to put it in the line there, and if you don't have the package, need to install. Okay, very nice. Yes. So let's the airfoil example, and you did this exercise with the a simple linear regression. There will be time here to continue working on this in a little while, but I can just, while I'm here, it can be interesting to just look at this example a little bit. So in connection to the different types of models that we talked about. So if I run this, it was this synthetic data, the cosine of x, cosine plus cosine 2x plus some cubic x to the third times something with some noise on it. And we get these losses. And the model we have here as sort of default is Gaussian processes. Okay. I can take away the picture there. So we have three of them alternatives stacked up here. Gaussian processes is the one that's run automatically, but then we also have the decision tree. So if we run that, you can see, let's say I remove these points that are plotted and run it again. So you can see here what I was talking about, that the decision tree model is a piecewise linear, piecewise constant. So it has a constant value on each and one of these intervals. And that's how the model works. And what the training and learning procedure is to find suitable intervals and values of the function. And of course, if you're in higher dimensions, more inputs, but still one output, you have to find the squares or rectangles, and in 3 dimensions will be cubes and what is called cuboids, rätblock in Swedish. Now I'm not sure what it's called in English, but like a rectangle but higher dimensional. So that's interesting to see. And if let's have a look at the random forest model. You can see that it's kind of squiggly as well. This is now the average of a lot of these decision trees. So it's a bit uneven. You can compare to the Gaussian process. It's very smooth and nice. You can try later to see how can you sort of plot these confidence intervals that I was talking about. It will be for each point you will have a standard deviation as well. It can be interesting also to look at, we have the decision tree here again. What happens if we have more points? Say 2000 data points. Then we get much finer. We have more training data. We get a much finer division here of the input space in smaller and smaller boxes. Okay, so we should continue with some exercises in 5 or 10 minutes, but I can move on and show you quickly another example here. So this is that was that about the nonlinear models, and you will continue with the exercises there, and also have a look at this material if you have time. There's a bit of extra material here on Fourier analysis, which could be interesting in the connection with time series prediction and so on. So we look, first there is a little illustrative example with linear models where we take a periodic function. So this is cosine of x plus cosine of 2x. So it's a periodic wave. And it has a fundamental frequency and one harmonic, which is twice that. In this case, I do the kind of usual thing here, take some input points and add a little bit of noise on the output of this curve here. So if we plot that one just to see what it looks like, it'd be interesting. All right. I do that. Plot this. So it looks like this. You have not a periodic curve, which goes like this, and then some noisy points around it. And the question here, can we sort of break this down into components? And one way is to use linear regression in the style that we did earlier with basis functions. So, for example, if we create our data frame with input and output variables, and we do our formula is like this, for example. We have the constant term, we have the component cosine x, 2x, 3x, and 4x. So that's our candidates. We can go further to see if there's any higher frequencies. But if we stop here and do linear regression on this, the output we get is down here. So if I run it again, we get this familiar statistics box with our coefficients. And here you can see that it thinks that the intercept should be kind of small. There is almost 1 here on the cosine, almost a 1 on the cosine 2x, and then the other ones are 0. So that seems reasonable. So it manages to pick out these components, the fundamental and the harmonic, to periodic functions. So that's pretty cool, I think. You can see that there.
May I make a remark?
What's that?
May I make a remark? If you look
Yeah.
at the plot, then you see that there are deviations. But if you now would plot the residuals, you see patterns, and then you might decide, hey, there are more frequencies in it than I have put in there.
Yeah, very good. And since we added noise, there will be some high frequency stuff in there. Yeah, very, very high up. Very good. So let's, as a last element here, before the exercises, have a look at Fourier analysis in Julia. So there is a package called Fast Fourier Transform W. And we can do this particular example, or a similar one, let's say. It's not exactly the same, to see how we can use this package. And here I do a similar thing as before. I start with some input data, and then I just synthetically generate a periodic function. In this case, it's cosine of 2 pi x, and so that's the fundamental, and then cosine of 5 times 2 pi x, so 5 times that. And we add some noise to it. I plot this and display. And then, no, let's see, right. We create a data frame of what we have up to frequency 5. Here, now let's see, 6 actually. And so what goes into that is cosine of 2 pi, cosine of 2 times 2 pi up to 6 times 2 pi, and also the noisy data. And we do linear regression on this as before. So this is a similar example to the one above. So let me just run this to see what happens. So we can do it until here. Okay. So this one is maybe a little bit more interesting. Looks like this. We have the noisy data around it, and we did some regression where we found the first component, and almost everything is zero except for the fifth component, and then the sixth one is zero as well, or close to zero. So that works similar as the previous example. And then we do to experiment with the FFT package. We do fast Fourier transform on the noisy data. So this breaks down the noisy or the data into components, finds the frequencies, and we can plot those afterwards. There's a little bit of what I call housekeeping here to get the right results. This has to do with the Nyquist frequency that, I mean, if the sampling frequency up here is 100 hertz, and you can only represent signals with roughly half that frequency. But you don't have to bother too much about this. It's to get the right results out of the fast Fourier transform. But if we plot that in the end, we can see the frequency components. So let's see. If I run the whole script here, it goes all the way to the end where we plot the output of the fast Fourier transform. So here we can see it's basically zero here. There's a little bit of noise, and then it's got two peaks. These are the two components that we have, the fundamental and 5 times that harmonic. The noise here is, I mean, we added noise to the data, so there will be a little bit of disturbance there. We can try to have another line here where you sort of zoom in on the two peaks. There. So that's what it looks like if you look closer, and we see that we have 1. This is the fundamental. That's the 2 pi x, and then we got 5 here, which is the 5 times 2 pi x. So I think that's pretty interesting and reasonably easy to use. So let's see. Let's do some exercises now for 15 minutes. The exercises you can do, you have, well, maybe some more of these on the simple linear regression example. And you can also have a look down here after the Fourier material. There is an example with the weather data again, but now using Fourier analysis to do regression on this to fit to the curves. Yes, so exercises for 15 minutes.
Okay, it is 10 past 11. Welcome back. Let's continue to the next episode about the scientific machine learning.
Here I want to give a very brief overview of what the scientific machine learning is and what you can use it for, and also how to do it in Julia. So we have there is a package called, look at that, SciML Julia, or is a collection of packages. So SciML, open source software for scientific machine learning in Julia. So here you can find all kinds of resources on this topic. And there is a lot happening here. So if you're interested in this, I recommend going through here and looking at the various tools that you can use for this. And in general, it's about mixing scientific domain knowledge with data-driven methods. So what we've been looking at here so far is with the regression examples is data-driven mainly. So we use data to fit models to them. But here we want to also use pre-knowledge that we have. We might know something about the physical system that we're describing. I have a little example here which sets up a dynamics problem. And it's an object, in this case a spherical object, moving in a viscous fluid, and it will be influenced by various forces. For example, you have the drag force that comes from the fluid, a little bit like air resistance. If you drop something from an airplane, let's say, there's a force pulling it in the opposite direction that it's going. And there will also be gravity pulling this object down, and one other force, which we'll look at closer later. And we look at this in 2 dimensions. So we'll have an object moving in the plane. So I have a little bit of slides here first on background on scientific machine learning. So these are the same slides as we had before. You can download them from the lesson material. The next section here is scientific machine learning. And as I said, in general, in scientific machine learning, we mix domain knowledge with machine learning algorithms. And so we model some phenomenon using both rules or laws of nature, for example, and data-driven techniques. And the way I see it, there are 2 at least applications where this is used. And one of them is where we have a physical system, maybe like our sphere moving in the viscous fluid, where our knowledge about the physical system is incomplete, and it needs to be completed with observational data. So you have maybe some measurements and stuff. You know some of the physics, but not everything. And if you think about this, it's actually rather realistic in the sense that we might have a physical model which is good, but it's maybe a bit idealized. So reality is not exactly like that. And then we try to make it even more realistic with using measurements that we have of the actual behavior. So that's one application. So that's interesting. And the other one is, the way I see it is, you use machine learning as a way to solve differential equations. So that's what you usually use for physical modeling in classical modeling. And so you know basically the equations, you know everything, but instead of using traditional solvers like finite element methods to solve the partial differential equations, you can use machine learning to do this, and with an extra twist, and that is that you can also simultaneously fit the model to observational data. So you may have, again, some measurements of actual solutions to the equations, and you try to solve the equations and also make the solution fit to the data simultaneously. And there's a kind of balance between these 2. And that's a little bit different than classical modeling. And again, the reason maybe the data and the actual solutions do not correspond exactly is that perhaps the model is a little bit wrong, and you get a balance between the model and the data. For the first application, typical tools used are the UDEs, so universal differential equations, or you might have heard of these or will hear about them, and it's good to know a little bit about what they do. UDEs is one, neural ODEs or NODEs, or neural PDEs and PDEs. So they can be used for application 1, and in the other one, I would say PINs, physics-informed neural networks, is a common one, but there's no strict boundary between these really. It's PINs, physics-informed neural networks, can also be used for application 1. So in this example that I talked about, we look at mainly application 1 here. So we have physical data information, but we don't know everything. And in this case, you can use a neural network to model the actual equation system. So that's the trick here. You don't know the equations exactly, but you can use a neural network to model the equations and use the observational data to try to extract that information from the data. Plus, you may have a little bit of knowledge that you add in yourself. So, for example, you may know conservation laws, like conservation of momentum or energy or something else, which you know must hold. And then you can impose this as a kind of constraint on your model that, yeah, it should also fulfill this, apart from fitting to the data. Or, you know, some other property. So you can see how this mindset goes beyond what we think of as physics. You can have any phenomenon that you want to model, and you know something about it, not just the data, but you have some rule that should be fulfilled. Then you can try to impose this on your model. And if you think about it a little bit, in typical machine learning examples like computer vision or something like this, where you detect objects in an image, the models in the end that are actually used for this, they are adapted to the domain in the sense that you're using domain knowledge with this, if you have seen this convolutional neural networks and things like that. It's not what you might call pure black box models where you just plug in the data and nothing else, but you put in a little knowledge about it as well. So one example, another example is that you have an equation system, you know some of the terms, but you don't know everything. And that's one such situation is where you know some of the forces acting on an object, but not all of them. And I have here 3 ways that you can try to get a property to be fulfilled by your model. And one is that you try to encourage this via the loss function that we talked about. So you kind of add a term which says this property should be fulfilled. If it's a conservation law, this quantity should be constant. And it tries to encourage that in the sense that balance it against fitting to data and other things. Another thing you can do is really enforce this via the structure of the neural network. So you choose your neural network in such a way that this thing you get out automatically satisfies the property that you want. And a third way, which is what we look at here, is you kind of help the neural network along the way with a little bit of structure, so that it in the end needs to learn a less complicated function than it would otherwise if you didn't put in any knowledge. So for example, it may look like this. You have an equation system. Let's put the derivatives on the left-hand side. So this y1, y2 are your state variables. So in our case, it would be the position and velocity of this ball moving in the fluid. And you may know some terms in each and one of these, so known terms, 1, 2, and so on. And then what you do is you write them in explicitly, and then you add on a neural network here, which sort of takes care of the rest. Down to the last state variable. And this can be done with universal differential equations or neural ODEs, for example. Okay. Okay. So this example, it's a bit long here, but you'll playing around with it in the exercises as well. So the first thing we do here is, if we go back to this ball moving in the viscous fluid, is to set up the ground truth equation system that we'll generate synthetic data similar to the earlier examples, and then we try to fit a model to it. And you need to define a function. There's a bunch of packages used for this here. They come mainly from the SciML library. And you'll need to set up a function defining your ground truth dynamics. This is to be able to generate the data to train on. And it takes the state variable, this is the position and the velocity of the object. And actually you can see here that the first two are the velocity and the position of the x coordinate, and the third and the fourth are the y position and its derivative. So there is a little trick here, standard trick to reduce the first order system. We don't have to bother too much about that. This is the interesting part here. This defines the dynamics of the object. So on the left-hand side, you have the derivatives of the first and third component. These are the acceleration of the object. And on the right-hand side, this is Newton's second law. You have the forces acting on it. And the first term here is the drag force. It looks like this. And then there is gravity, which is pulling it straight down. And then there is the kind of secret force here, which is the last terms, which I will return to later. And if you have such a system defined in a function, you can set up a ODE problem. So ordinary differential equation, plug in your function, plug in an initial value. This is something we just pick randomly here. This is the initial position and velocity of the object. And solve that over a time span. So that's done with this solve function. You specify the particular ODE solver you use, Vern 7 in this case. We can just plot that to see what it looks like. So I run that code and we get this. So this plots the journey of this little ball at evenly spaced time stamps. So it sort of seems to go slower here at the beginning and then goes faster, but seems to approach a constant velocity here. We can run it again with different initial values. We see a little bit more the curve that it takes here. So that's pretty nice. And let's have a look at those forces one more time. So we had this section of the dynamics. This first one is the so U1 and U3. These are the velocities of the object. So this first factor here is its speed. So we got the speed times the velocity vector. That's the drag force, how it works on a spherical object. So it actually scales as the square of the speed. You might remember that or have heard it. As I said, the gravity is just pulling it straight down, so it doesn't have any component up here. And the last term here is something I added to make it a little bit more interesting. And that is what kind of force would act on a charged particle moving in a constant magnetic field. So if you add a magnetic field that points straight out of the screen, what is otherwise constant, you'll get a force which is perpendicular to the velocity of the particle. Like in one of these particle chambers, you can see the trajectory that the particle is moving along. So this will twist it. The force is perpendicular to the velocity. That's what this here represents. So let's see if we can model this with a universal differential equation. So in this case, we forget all about the physics in the first case and use a kind of black box model where we try to model the entire right-hand side of the equation system, all the forces without knowing anything about them. And we'll use the data generated from this underlying model to try to fit a model to the right-hand side of the equation system. So what we got is the same thing as before, computing our training data. And then we need to set up a neural network that emulates the forces. And that's done similar to before. Here I call it U, and it's a chain of 1, 2, 3, 4 layers here. So it takes 2 input variables, then there is a 5 to 5 layer, and a 5 to 5 neuron layer, and then 2 out. So why is it just 2? That seems weird. It should be 4, right? I mean, we take the position and velocity of the object, and we spit out the acceleration. And that's because I forgot to say something here, which is actually interesting. We'll do this under a particular assumption. So we'll assume a prior knowledge of what I call homogeneity. So we assume that, as is the case here, the forces acting on this object only depend on the velocity, not its position. So that means that the viscosity is the same everywhere and this magnetic field is constant. Otherwise, it would depend on the position. But this illustrates a little bit how you can put in things you know or make assumptions about it into the model and enforce it. So in this case, we'll only have it depend on 2 variables. These are the velocity variables. In order to use universal differential equations to model this, you need to define your own function here, which basically tells you that you want to model the right-hand side of the equation system using your neural network U. So this takes U in and it evaluates the neural network on the first and third components. These are the velocities. And it spits out the acceleration, which is given just by the neural network here. And it's the same trick to reduce the first order system. But you don't have to bother too much about that. So what do we do? So how do we use this? It's basically we have our tentative equation system, then which is governed by the neural network, and then you need to solve that, see what the solution looks like, compare to the ground truth data, compute the loss function, and train on that one. So that's done in these few lines here that follow. We have a function called predict. This solves our equation system, which is the model that depends on the neural network. And the loss function compares the result with the training data that we had. And then we use an optimizer. You need to put in your loss function into the optimizer to find the so-called optimization function and an optimization problem. And epochs is the same as before, the number of iterations that you do. And in the optimization package, you can do optimization.solve. You specify the specific optimizer that you use here. So this is a bit fast, but it's an overview. You can try the code a bit later. So let's see. When you solve the optimization problem, you get you can store the results, and that means you get the parameters of your neural network out of it. That's the p-trained. And then we can plot the results. We will plot the original orbit that we used for training, and we'll also plot a test trajectory, which means we don't test on points. We talked a little bit about testing and training. We have this one orbit that we're training on. We're not going to test it on points along this orbit because that's too easy. So we take another one which has random initial values, random position and velocity, and we see how it goes there for the model. So let's see. Let's run this. See what happens. So it's, yeah. So it seems to go through the iterations here. The number of epochs was 1,000. And the loss is decreasing. And there we go. So let's see. This is kind of telling result here. We got the true data points, which are green, the prediction, which are red. The green ones are sort of underneath here. Those are the dark red ones. And there are red ones on top of them. So these are our training orbit. And then we have the test data, which is blue, and the predictions on the test data, which is yellow, that goes way out here. So you see, while it's doing well on the training data, on the test data it's doing very poorly. And we can try, let's see. We can try to generate some more test orbits here just to see what's going on. If I generate a new test orbit randomly and do predictions on that, I get this and that. And that was pretty okay, and so on. So the model is clearly not ready. And one explanation here is that we only trained it on one initial condition along one orbit. So if we change that, that's this line here, which generates initial values for the training randomly. And we only took one, that's this last one. So we can take 6 of those, see what happens. So let me just run the same thing, but with a 6 there. So now it's started. And it's much slower now, as you can see, because it has to solve these 6 equation systems, put everything together, compute the loss, predict on all of those 6 initial values, compute the loss, and do the compute the so-called gradient of the neural network on that whole thing. So the more initial conditions you put in here, the slower it will be to do each step. But now it seems to be down at least 10 to the minus 5 or something. So, okay, so since I changed the code a little bit here, we only see the test orbit. I can plot everything. I think, yeah. So this is everything, including the training data. So we see now we have our 1, 2, 3, 4, 5, 6 training orbits. So it's trained on all of these, and then we got the test orbit, which is now pretty stable, or it's the predictions are pretty good on that one. So you see how you might want to, in some sense, cover your space of initial conditions in order to get good generalization, because if you do it too narrowly, it will not generalize well to other situations. So we can again plot some different test orbits randomly chosen. This one, there is a little bit of deviation there, but it's much better than before, at least. It looks pretty good. Okay, so let's see. Wow. 10 minutes. I think we should, since we want a little bit of time to wrap up as well, it makes sense to do some exercises. I will just show you briefly. There are two things here. One is what I didn't get to now, and that is you can try yourself. In the example I did, I used a kind of black box model where the neural network models the entire right-hand side of the equation system. You can do what I talked about before, help it along a little bit. So you put in some of the forces, like the drag force, and you let the neural network take care of the rest. So it has to discover gravity and this Lorentz force, which is what's acting on the charge particle in a magnetic field. And you will see that this works as well, but it will be much faster because it gets this help from putting in the drag force explicitly. And then we have a few exercises down here that you can also do. Yes, I can. So a recap of the, let's see, all the episodes, right, of the workshop.
Yes.
Yeah. Okay, so we talked about data formats and data frames. We learned how to use these tools in Julia, which is similar to Python, how to load data, and how to change the different data formats and manipulate data frames. And there was a section about linear algebra, where we saw how to do vector and matrix operations, and how to also compute eigenvalues and eigenvectors and apply that to principal component analysis. So the connection between linear algebra and data analysis. And then we had a section about when we started with the regression, I talked about linear regression, so linear models in one or several variables, so univariate or multivariate linear models, and also how to do linear models with basis functions. So this trick that allows you to model nonlinear relations with still using just linear regression. And then today we talked about nonlinear regression, so neural networks first, how to use that in Julia with the Flux package. And then we talked about how to use the MLJ package. So this is, you can do it for neural networks, but I showed some other nonlinear models like decision trees, random forest, and Gaussian processes. And at the end, we did, and I talked a little bit about Fourier transform and Fourier analysis with the FFTW package. And then here at the end, we did a quick quick overview of scientific machine learning. So how to mix physical models with data, and basically how to mix pre-knowledge that you have with observational data that you have measured about your system. So that's the summary of the lessons that we did.